guys, so I'm going to try to get through 2 more sections. Finish out chapter 7.
Remember, we have to do the homework, too.
We're going to do what I just said.
2 more sections of 8, right?
I appreciate your
1 and 8 too?
suggestions, and we'll file them away. Oh, sure. You got it done, yeah.
Okay, I can accept that.
And guys, a quick suggestion on homework. If you're behind in earlier homework, let it go for right now. Get into the new stuff now. Catch up on the old stuff when you can. If you have a lot of old stuff, see me. And I'll try to get it so you can still get practice, but not as you don't have to do every single thing. Make it a little quicker. So you still have to come see me. Okay? 7-7 involves one idea. They are word problems, but they're actually relatively easy word problems. Remind me this. What's true here? A squared plus
B squared.
Cool, right? And there are actually like hundreds of proofs for this. In fact, one of the Roosevelts, I can't remember which one off the top of my head. I think it was Teddy Roosevelt, one of the presidents. He was kind of obsessed with coming up with new proofs for this, to tell you honestly. It's kind of nice to know that one of our presidents was a major geek. At least for me. I don't know. All of 7 is really related to this idea. So let's do a couple of examples. Right? There are word problems, but they're really just put the right number next to the right side and fill it in. It's not that bad. A very direct problem. What if I had this kind of problem? Solve for the missing side. So if I had this kind of problem here, can you set that up in an equation? Yes, I like it. See, not too bad. What's sort of the most important side in a triangle in a way? When you're trying to set up this thing. What is it? Hypotenuse. Because that's the one that has to be by itself. It kind of makes sense. It's going to be the longest side, so it's the one that's equal to the other 2 sides put together somehow, right? So what would this look like then? It would be, all right, x squared plus 7 squared equals 11 squared. So not too bad. I mean, these equations in this section are just, you hope to God all equations are like, this is not bad at all. You can kind of get away from factoring because you're not going to be able to factor a lot of these. Just go directly to the square root. These are sides of triangles, so do I have to worry about the negative root? No, because they're sides of triangles. You can have a negative side of them. So what I want to do next? 72. Square root. Now the book is going to say, and a few of these problems are going to say, give an exact answer. And people often have the wrong idea. That's the exact answer. And then it says, give an approximation out to 3 places, or whatever. Then you plug that in your calculator and see what it says. What should this be in between?
8, 4, 5, or 45.
So it should be between 8, because that would be 64, and 9, that would be 81. So it makes sense to be 8.4, blah, blah, blah. I love it. Right? So x to the square root of 72, which is approximately equal to 8.4, whatever the hell.
Do we have to simplify it, right?
Yeah, I was about to say I love it. I don't think it really makes a point of it here. No. But you really should simplify this. How could you break up 72?
36 times.
I love it. 36 times 2. Square root of 36 is 6. Square root of 2, I don't know. And if you did 6 times square root of 2, it would become that.
But do we have to do that?
You should, actually, yeah.
Alright.
Because especially if you're going into pre-calculus, but even if you're not, you have to do it for me anyway. You're going to desperately have to. It almost should become like if you get 8 over 10 as an answer, that's not right. If you get square root of 72 as an answer, that's not right. It hasn't been reduced yet. Right? I like calling this reducing the radical, really.
It's just hard to find out on your calculator when it's a big number if there is anything that can be squared. What is that?
You just start dividing it by squares. Because you know you want to try to break it up to a square times something. So 72 divided by 4, 72 divided by 9, 72 divided by, right? 36 is the biggest thing that goes into it, though. Yeah.
That's what I was going to ask, too, because you can do 9 and 8.
I love it. So if you do square root of 72, if you do 9 and 8, square root of 9 is 3, square root of 8, but 8 is 4 times 2. So it's sort of like reducing a fraction. If they're big-ass numbers, don't you have to do several reductions sometimes? All right, so big-ass number, you have to do several reductions. You'll still end up with the same. It'll be 3, it'll be 6 root 2. It's the same answer. Yeah, it just doesn't matter as long as you keep going until it's done.
So
Yeah.
you gotta like memorize a table in your mind of what squares and cubes are.
You should have that. You really should. You should know your squares up to at least 12. Everybody knows 12 squared. You should know your cubes up to at least 5, if not more. And we've seen 125, and that's 5 cubes, right? We've already seen them when we were factoring cubes, factoring squares. Yeah. You should know your 4th powers. Right? A few, maybe up to 3 or a little bit 4. Yeah. Let me show you, let's look at a wordy problem here. Like number 19. I haven't even read this yet, let's see. Claire bikes across a rectangular parking lot on her way to class. She rides it exactly diagonally. That's awesome.
Page.
What's up?
Page.
Oh, page 590. If the lot is 200 feet long and 150 feet wide, how far does she travel when she goes across the lot? This is a rectangle, right? So I know that I have the right kind of triangle when I break it up. Of course, what kind of triangles does Pythagorean theorem works with? Right triangle. So I know this is a right angle, even if my picture doesn't look like it. So go ahead and try to set that equation up. I think most of you guys are. This one should come out to a whole number, right?
Mm-hmm.
Yeah. What's that? 1, 0, 0, plus. No, something wrong. Oh.
22500.
I was trying to put it in parts. And then you add those, you can actually do the square root of it. So 62500.
250 feet. Feet.
Yeah.
Don't forget
Good.
that feet.
Yeah. Do you guys know right triangles have whole sides? I mean, fewer and fewer people know about this. There are certain triangles that, like 3 and 4. 3 squared plus 4 squared is 9 plus 16 is 25. Square root of 25 is 5. So you got a 3, 4, 5 triangle. Now watch. If I multiply this by 50, if I make this triangle 50 times bigger, what's got to be true? How big does this side have to be?
50.
So imagine that's 50 times bigger. That would have to be 150. That would have to be 200. And this would have to be 250. Now I have to go through all this shit, right? In fact, they love to put that kind of problem on a standardized test. GRE, SAT, whatever. They love that kind of what's called a Pythagorean triplet, or I don't know what the hell else you call it. We call it Pythagorean triplet because it's Pythagorean theorem, sort of, and there are 3-figure numbers, right? So another one would be 5, 12, 13. 5, 12, 13 triangle. Fewer and fewer people know about this kind of thing, though, which is too
Say it
bad.
again, what you just said.
So there are very few of these right triangles that have whole number sides. And that shouldn't be a surprise, because if I just come up with 2 arbitrary numbers, it's probably going to have a square root at the end, right? These have got to somehow become numbers that when I add their squares is itself a square. And that's not going to happen very often. Are you guys kind of with me here? Maybe not. Come up with, give me 2 numbers.
7 and 4.
Sigyn?
Any number?
Any numbers.
7 and 4.
7 and 4, I love it, right? Let's make it look more. What's 7 squared plus 4 squared? So it'd be 49 plus 16. 65. And what's the square root of 65? Is it something nice? No. So you come up with any 2 arbitrary numbers, and more than likely, you're going to get an ugly last side. You guys with me? It's very interesting that there are a few that happen to come out with a nice whole number side. There's 3, 4, 5, there's 5, 12, 13, there's several more. And if you know these, this kind of problem is quick, because that's what I always check first. I'm like, okay, that's 50 times 3, that's 50 times 4, oh cool, that's 50 times 5. Because it's just 50 times bigger than that standard triangle. If you don't like that at all, okay, we can do it this way. That's fine. Yeah.
You would just have to know those numbers though, because
Exactly.
so you wouldn't, like, if you see that those 2 sides have a common factor.
A common multiple, yeah.
Can you make that into a?
It's kind of like
problem?
reducing those to see if it matches up with one of your known trends. And that's why I hate the fact that memorization nowadays is so such a villain, and it's stupid. I mean, some memorization is necessary, and then even a little bit more, it makes things quicker. I don't have to do any of this shit then. I can just go, bam, bam, oh, it's 250. Next problem, please, right? But memorization is going out the door and just kills me. But you still have a way to do it if you don't like memorizing 3, 4, 5. Okay. And really, they're not going to make this, every single problem is basically that. I know it's a word problem when you look at it, but just see the numbers. Where's the number go? Where's the number go? What do I not know? Set up the equation. They're all Pythagorean theorem. This section's nice, actually, believe it or not. A nice word problem section. Those exist. It's crazy. So I'm not gonna waste any more time on that. I can't make it harder than that. That's all it is.
You say you can't make it harder than that?
Nope.
Can you make it easier?
Sure. Of course I can.
Just give you the section.
Let's see. Last section for today, and I'm basically gonna get just a little bit into it, and we'll get out of here a little early. So I don't want to hear any moaning, or any more that's already happened, I guess. The good appropriate term is complex numbers.
Oh, great.
And that's made of a real number and an imaginary part, or an imaginary part. The term imaginary was an unfortunate choice, because nothing turns students off more than having their worst nightmares verified. Making a you're making this shit up. It's imaginary. You just said right there it's imaginary. What the freak? It's really, really difficult at this level to talk about the uses of complex numbers, because they require like exponential equations. When we talk about exponential equations, it can come back and talk about complex numbers a little bit. Because remember me, I think a few of you guys were musicians, and a few of you guys knew what I meant when I showed you this, and the gain thing. It was, if you picked up too much, remember I said it inverted it, just so it doesn't lose. I don't know if you guys were here that day. But any wave like this, these are called sine waves or cosine waves. Well, trigonometry, but oh well. There's actually an equation you can write in terms of E. I don't know how many of you guys know about E. It's like the number pi. And I. Well, that's coming up later. Right? And this is what I mean. It's very difficult for me to give you the full story of why imaginary numbers are useful because we don't have the math yet to do it. We have the math to do complex numbers. The math for complex numbers is stupid easy. Why we need them, well, that requires further math. Right? One little thing is anybody wants to become, I think maybe some people already are, engineers, electrical engineers maybe, or computer engineers maybe. In electrical engineering and engineers in general, they don't use the letter I for a measure, they use the letter J. But it's the same thing. If you want to talk about you ever unplug the vacuum cleaner when it's still running and you see the little spark? Right? And that's a voltage wave. It's trying to maintain that current. It doesn't want to lose it, so it's trying to do everything it can to keep it going. And then you pull it too far away, it's like, The equation for that current going through there requires the use of imaginary numbers to fully describe it. Right? And again, I can't show you the math. It's a little bit uglier than we need to see. But I always try to give you reasons why we study some of the stuff that we study. So complex numbers have, like I said, a real part and an imaginary part. Doesn't belong in Foster's. Have you ever seen that show? There you go. A plus BI. So every single number we've seen so far has been complex, where B equals 0. Right? Because, for example, if A is 2, and B is 3, what complex numbers does that make? 2 plus 3i. But we've seen the number 7 in here. In fact, they just had it up here somewhere. There's the number 7. But isn't that 7 plus 0i? Maybe. So just like every single whole number, every single whole number is natural. Every single rational number is also, every single whole number is rational, right? So like 7, I can put it over 1. Every single real number is also complex. It's like the big group. So a real quick little review. There are natural numbers, right? 1, 2, 3. Then there were whole numbers that start at 0. Then there were integers. Then there were rational, irrational. All of those freaking things are real, right? And all those freaking things are complex. So this whole circle here with the real circle, they got a better picture in the book on page 595. It's more like a hierarchy thing. Everything in this real circle has B equal to 0. So everything out here, like in here, there could be 6. Out here it could be maybe 6 plus I. Maybe some of you guys get where I'm coming from. So every number we've seen is a complex number with no imaginary part. So that's why we call them real numbers, because that means it must only have a real part. So here's the nice thing. I'm sure you guys are waiting for a nice thing. Here's the nice thing. Actually, before I get to the nice thing, I haven't even talked about what the hell I means. What is I defined to be, or what is defined to be I? I love it. The square root of -1. So the very weird thing about I is, what do you get when you square it? You get -1. So that's why I was saying earlier, I was trying to be very careful when I said earlier in this class, there's no real numbers you can square to get negative. I had to say that real, because there are definitely complex numbers you can square to get negative. Okay, cool. And real quick, just to kind of keep going here. So I is -1. I squared is I times I, which is, square root of -1. I squared is -1. What's I cubed? build it up. Isn't I cubed I squared times I? You with me? Of course it is, because 2 plus 1 is 3. What's I squared?
Negative 1.
So I cubed is negative I. I squared is what? What's I squared? Negative 1
I'm negative 5.
times I is negative I.
Okay.
Stay with me now.
Nope.
It's not that bad. You don't even have to know that I is a freaking imaginary number at this level. What's I cubed? I squared times I. You can't argue with that. I squared, we just discussed, is negative 1. Is everybody cool with that? I know it goes against everything you've learned, but not really, because we've always said real numbers can't become negative when you square them. These aren't real. They don't have to follow that rule. So now we know I squared is negative 1. I cubed is I squared times I. Negative 1 times I. I cubed must be negative I. So what's I 4? I to the 4th power.
1.
Why? Here's a nice way to do this. I squared times I squared.
Negative 1 times
And I squared is negative 1. Cool. And then it starts over. Do you see how now it cycles? What's I 5? It'll be I 4 times I. 1 times I is I.
Does that on I3? Does that say negative 1 at the end or negative?
Negative I, sorry. Yeah. Make that a little curlier. Alright, so that's one thing about I. Just because of the way we define it, I can then do this to it. Right? The most important thing in this whole thing is this. This whole list. This whole list is important, but the most important thing is this. Because he's the one that occurs the most. So let me show you why that's true. So here now finally is the nice thing about complex numbers. A couple nice things, believe it or not. What does your gut tell you? 4 minus 2i plus 3 plus 7i. So I'm adding two complex numbers.
7 plus 5
Plus
I.
3.
Right? Just put your like terms together. So I is like a variable. It's a very specific variable. It's sort of like pi is not really a variable. It's a very specific letter. It represents a single number. I represents square root of negative 1. What is the square root of negative 1? I don't know. That's why it acts like a variable. Just combine your like terms. Here's all the real stuff I got. Here's all the imaginary stuff I got. That kicks ass, right? The next level would be so I can have a bunch of numbers like that. Big deal. Who cares? If I had like 8 plus 7i minus negative 4 plus 2i, what do you got to do first? Distribute the negative. I mean, come on. Now this level is like polynomial like term business. Who cares, right? Distribute the negative. 8 plus 7i plus 4 minus 2i. 12 plus 5i. Cool. Okay. Awesome. Now you might think, and you'll be right if you think that foiling and stuff is equally easy. It is, except we got to realize we know more. What is x squared? X squared. What's I squared? Negative 1. So we're able to do more when I get an I squared term. We can replace that with negative 1. I does not equal negative 1. I squared equals negative 1. Be real careful. So for example, you guys try this problem. One extra step than normal, because these aren't variables, they're imaginary numbers. So the first step is the same as always. What do you get?
24 minus plus 28 I plus 7i plus 15.
Minus 15.
I'm with you, so let me catch up to you. Sounds like it takes a long time. So here I can put my like terms together, but I squared is -1. So you got 24 plus 2i plus 15, so now I can put those together. So there's a slightly larger concept here. Whenever I multiply or add or subtract complex numbers, the answer must be a complex number. And what does every complex number look like? A plus bi. That's why it makes sense that something more should be able to put together so I can get a plus bi as my answer. Don't I have that? A is 39, b is 2.
That's a complicated question. If you were to put the 7 plus 5i, if that was in the denominator, would you replace the I by the square root of -1?
Oh, I
and
see. Well, that's funny.
do that
Okay.
step that we did?
That's so funny. Because the last thing I got to talk about is how would you do I minus 3 divided by 7 minus 4i. And actually, we just talked about this earlier today. Because like you just said, you don't have to replace it. You just have to know what it is. I is a radical, isn't it? It's the worst radical possible because it's one I can't do, it's imaginary. But still, it's a radical. So to be able to do this, I have to multiply by the conjugate. In this case, amazingly enough, it's called a complex conjugate because it's freaking complex. But what would it be? Multiply by?
7 plus 4i.
Exactly. Because when I divide or subtract or add or multiply complex numbers, it better end up being a complex number. A plus bi. This, at the end, better look like that. It better look like A plus bi. So see what we get here. We get 7i plus 4i squared minus 21 minus 12i. Cool. Just foiling over 49 minus 28i plus 28i cancels. Minus 16i squared. Everywhere I see an I squared, it's actually -1. So I get here negative 5i minus 4 minus 21, right? Because that's a -1. Over here I get 49 plus 16 because that's a -1, right? So I get 65. Because the biggest mistake I see is people will replace the I with -1. If I was -1, why the hell would we even have it? I wouldn't need it. I know -1. So here I get -5i minus 25 over 65. Now technically I would take that, but what did I just say? You have to be able to write it as A plus bi. So I can break this up. And then I can reduce, right? So you get -1/13 I minus 5/13. So there's my A, and there's my B, I. If you stopped here, it'd be okay, I guess, sort of, not really. You should take that further step and break it up. A plus B, I. Just one last idea I want to throw at you. The really cool thing about bringing complex numbers in is this. You guys ready for this? I'm going to blow your mind. What's the first step on solving that equation?
GCF. X.
Can you factor this? Not using real numbers.
No.
But I can factor it using complex numbers, right?
X.
So it would be x plus 4, x minus 4, but we know that's not going to work, right? Because I end up with a negative 16. I need a positive 16. How can I make the positive? I just put an I. Just,
Go back.
okay.
Okay, I got you up to -5i minus 25 over 65.
And then just break it up, of course, right?
Okay.
And and then reduced.
Oh, okay.
Yeah, 5 goes into 65 13 times.
Still one.
Right. So 5 65ths reduces to 1/13.
Okay.
25 65ths reduces to 5/13.
What about the I?
And the I is just sitting there. Right? I can't do anything with the I, can I?
Wouldn't it be over the 13 Yeah, wouldn't it be
Well, it's not.
so confusing?
It's not down under there. It's there.
Oh,
It's on the side.
Yes. Cool.
so the whole thing.
Isn't 3x over 2 is the same thing as 3/2 x? Thank God we know that because now I can see the slope, for example. Right? Yeah. Don't forget the old stuff when we start learning new stuff. The old stuff still applies. Now coming back to here real quick, just to show you this in a different way. If I wanted to solve this, couldn't I do this? And then take the square root? Now what's the square root of -16? Stay with me now. Isn't this the square root of 16 times the square root of -1? Isn't that true? And what's the square root of 16? 4. What's the square root of -1? I. Okay, there's your plus or minus 4i, right? So the reason why I said this is cool is because what did I say about things to a third power, things to a fourth power? How many answers should we expect?
3.
I kept saying at most 3, at most 4, real answers. When I introduce complex numbers, there has to be exactly 3 answers for anything that has a highest power of 3 equation. If I have a 7th power in there, it's got to be exactly 7. Some of them might be real, some of them might be complex. Right? So it really completes that whole idea. When I have a cubic in this problem, if I were to solve this before today, we'd have 1 answer. X equals 0. Right? But now we get 3 answers because this guy gives me 2 complex answers. So my answers would be 0, -4i, +4i. Yep.
How did you get the -4i? Because wouldn't 4 times -4 be -16?
But this is 4i times -4i. What's 4i times -4i? -16, then yeah. What's I times I? I squared, right?
Yes.
Of course.
-1.
Yeah, so -16 times -1, 16. So the problem up here was there are no real numbers that I can multiply by itself to make a positive and have the middle term cancel, right? So here I've got these two that are opposite signs, but when I multiply, they are positive because that I squared makes it positive again. So what do you think about this? What's the square root of -25? 5i. You just go, what's the square root of 25? 5. And then you throw an I in there because it's complex. Cool?
Sure.
Oh, hell yes. How do you factor x squared plus 49?
X minus 7.
-7.
X by 7i, x plus 7i. You throw that I in to make it work. You know it's got to be imaginary because there's no way to do this using real numbers, but I could definitely do it using imaginary numbers. Okay, cool. I slowly convert people to my side. Right now? Really?
No,
Friend of ours.
All right, guys, that's plenty. So next time we'll get back into complex numbers. There's still some more stuff in that section we have to do.
Imaginary -1 in math 9. Deep breaking out.
Yeah.